Hello, everybody. My name's Cooper, and today I'm going to be going over my presentation, which is solar flare analysis using machine learning. I use the NASA DONKI solar flare dataset. Um, so, yeah. So the first question that we're going to deal with is what are solar flares? And solar flares are basically these huge bursts of energy that come from the sun. They happen when the sun's magnetic fields get all tangled up and then suddenly kind of snap and release energy. So, a lot of people compare it to a rubber band snapping, which is actually a pretty good way to picture it. These events are super powerful, even though the sun is really far away from us. The energy from a flare can travel all the way to Earth and mess with things like satellites, GPS signals, radio communication, and power grids. Um, The stronger flares, like I said, they can affect power grids, which is really crazy when you think about it. But the overall idea behind the project was instead of just looking at solar flares as random events, can we actually find structures in them using collected data? And more specifically, can these help us understand things like how often flares happen, how strong they are, how long they last, and how they evolve over time? Um, so, yeah, um, basically, we just want to understand, are the flares random? And can we predict or understand the flare behavior? So, the goals of this project are really pretty straightforward. First, I just wanted to understand whether solar flares follow any kind of pattern over time. Um, like, do they increase steadily? Do they decrease? Or do they follow some kind of cycle? We actually already know that solar activity follows something called an 11-year solar cycle, where activity goes up and down over time, but I wanted to see if that shows up clearly in the data. Secondly, I wanted to see if we could predict flare intensity using features we can measure, like duration, time to peak, location on the sun, and time based features. And then lastly, I just wanted to compare the different machine learning models and see which ones actually make sense for this kind of problem. This matters because flares aren't just academic. Um, uh, yeah. So this matters because solar flares affect real systems. So they affect satellites, they affect aviation routes, they affect communication networks. Um, an example of this is flights can be rerouted near the poles when there's strong solar activity. So understanding these flares results in better prediction methods and improved safety planning. So I used the NASA DONKI solar flare database, which is basically a big record of solar flare events over time. So each row in the dataset represents a single flare, and it includes things like start time, peak time, end time, the flare class, so CMX, the location on the sun that the flare occurred, and the intensity of the flare. Um, so what I found is that the data was really kind of messy at first. So like the times stored in the timestamps, um, they were stored as full timestamps. So I had to extract the year, the month, and the day manually. So some of the data wasn't useful for machine learning right away. So it needed feature engineering. So like I converted the raw data into machine learning ready features like the year, the month, and the date, flare duration, time to peak, and other intensity features. So one of the first things that I used was linear regression. Um, so I started with it just as a baseline, and one thing I was trying to predict was how many flares happen per year. And the model basically just drew a straight line and said something like solar flares are increasing by about 160 per year. But the problem is that's not actually how the solar activity works. In reality, solar flares follow a cycle. Roughly every 11 years, the activity goes up and down, so instead of a straight line, it should look more like a wave. But the linear regression basically forced a straight trend onto something that's naturally cyclical, so that makes the result kind of misleading. For predicting flare intensity, it also performed poorly. I don't have the image here for that, but it had really low and like even negative R squared values, which means it just did even worse than guessing on average. So linear regression really wasn't suitable for this problem. I moved on to decision trees, and this worked a lot better. So instead of trying to fit a line, decision trees basically ask a series of questions. So, like, we can use a set of simple rules like duration, peak speed, and intensity thresholds. And then it splits the data into groups. What I liked about this model is that it actually started to reflect real flare categories. So it started to show short C-class flares, medium M-class flares, and large X-class flares. And it got about 70 to 73% accuracy, which is pretty good for kind of like this messy world data. But the downside is that it overfit sometimes, so it would just memorize patterns too closely instead of generalizing. But this was one of the stronger models, so it still worked pretty well. The next thing I tried was logistic regression, but it can only classify into categories like small versus large. And I also had to balance the data set because I had so many M values which were small, that I had to add data to the larger flare intensities, so that way I could even the data set. And it got about 61% accuracy, so not amazing, but still useful. What was interesting is that it actually gave some interpretable relationships. So, for instance, shorter flares in duration equal more likely small flares, and then and then faster peak times equal larger flares. So it wasn't super accurate, but it was good for interpreting the data. I also used naive Bayes, and this one actually worked really well. It worked around 76 to 77% accuracy, but the big issue is that it assumes that all the features are independent, which isn't really true. Like for instance, duration is not equal to independent of peak time. Duration and peak time are directly dependent on each other, so they're not independent. And it also struggled with rare events like the X-class flares because there just weren't that many examples of them in the data set. So it worked well overall, but it had some clear limitations. For clustering results, I used different clustering. So I used k-means, I used density-based clustering and hierarchical clustering. And the same pattern showed up for all of them, which was awesome. And it basically just said that we have most of our flares as small M-class flares, and that were short duration and fast peak time. And then we had a few extreme X-class flares that stood out as outliers. So like, for example, the k-means, it clearly separated three groups when k was equal to 3. The density-based clustering found one huge cluster and a few small outliers, and then the hierarchical showed one big branch and then two smaller separate branches. So even though the methods were different, they basically all agreed on the same structure of the data, which was awesome. So our key conclusions here are basically just that the solar flares aren't random. They follow very consistent patterns. Most of them are small flares, and most of them have short durations. And then most of them have their peak intensity occur rather quickly. But then there's these high intensity X-class flares that behave very differently and stand out as outliers across basically every method. Another important point is that this is a highly nonlinear system, and that's why linear regression didn't work well. It basically assumes everything follows a straight line relationship, which just isn't true for this data set. The more flexible models like decision trees and naive Bayes worked better because they can capture more complex relationships between variables. One of the biggest challenges, though, throughout the project was class imbalance. Like almost 90% of the data was M-class flares. And so the models naturally tended to predict that category more often. And so you had to actively balance the data, which is kind of hard to do without skewing your data set. So overall, machine learning definitely helps reveal structure in solar flare data, but it also has limits, especially when dealing with some of the rare case events. But it just shows that none of the models are perfect, and each one gives you a little bit different sort of information on your data sets. So the final takeaway here is that machine learning can help reveal hidden structures in solar activity. But like I said, no model is perfect. Real-world systems are messy, cyclical, and imbalanced. And the conclusion is that you need multiple models to understand complex natural systems. So I hope that you learned something in this PowerPoint, and I hope you enjoyed it. And that's it. So thank you very much for listening.